All right, everybody. Hello. Welcome to the live stream. I'm going to get right into it today because I'm really excited for today's topic. Today, we're going to be classifying handwritten digits with neural networks. This is one of my favorite projects to do to show to beginners. This is a really cool way to understand how neural networks work while writing concise and simple code. So the dataset we're going to be using is called MNIST. Let me show you a little bit what that looks like. So this is the MNIST dataset. There are written digits, and the purpose of this video is to write a neural network that will be able to classify these handwritten digits. So I hope you guys will stick with me to the end. Let's get right into the code. All right, we're in the Kaggle kernel. You can open a similar kernel. I just prefer Kaggle because it's really easy, simple to use, and works really fast. Let's start with the dependencies and the libraries we have to import. So we have to import NumPy, and for today's neural network, we're going to be using Keras and TensorFlow. So after we import MNIST, which is our data set, and MNIST has its own library that we can call on, and I'll show you exactly how we call on that in just a minute. We need to import a few things from Keras. Two different, like a model, a layer, and a utility that we're going to be using. So the model that we're going to be using, tensorflow.keras.models, is our sequential model. This is the most used model for building neural networks with Keras and TensorFlow. The layer we're going to be using is the dense layer. The dense layer is a simple, fully connected layer for neural networks. It's the most basic neural network layer that you can build in Python. And that is going to be the layer that we use for our entire neural network. So import dense. And our last import, we're going to be using toCategorical, and I'll explain the function of that in just a second when we get to that part of the code. toCategorical. If you guys have any questions throughout the live stream, definitely feel free to ask me. I'm here to answer your questions. So let's get right into the meat of the code. So let's just run this to make sure that there aren't any errors, and we are 100% good. So with data in neural networks, we need to split our data into training and testing data. But before we figure out what percent of the data is going to be test, what percent of the data is going to be train, we need to load all the images into 4 different variables. And those 4 different variables are training images, training labels, testing images, and testing labels. All right, why do we need labels? Images are obvious. We need to classify the images. What are these labels that we're talking about? Labels literally label an image. They say this image is an 8. This image is a 7. This image is a handwritten. So it's very intuitive. We say MNIST.trainImages. This is already set up for us pretty easily. And then we say MNIST.trainLabels. So pretty straightforward. And then we do the exact same thing for test images, but instead of train, it's just test. I would say that's quite simple. All right, so train images to test images, train labels, test labels. Okay, great. Let's run that really quick. Okay. So we can't just give a neural network an image without doing anything to the image. We need to pre-process the image. We need to normalize it, and we need to flatten it. What does normalizing mean? So an image is basically a 2-dimensional array, and the elements within the array are pixel values. All right, pixel values between 0 and 255. All right. So this is what an image might look like. So you have, I don't know, a pixel that's value of 34, 56, 72, 21, 32, 58, whatever. And let's do one more. So it's 3 by 3. 21, 25, 27. All right. A neural network, it would take a lot more time to process this data if all the pixel values were values between 0 and 255. Normalizing our data, whether it's in neural networks or in data analysis, is taking our data that ranges from 0 to maybe 1,000 or 255 in this case, and compressing that data so our range is between 0 and 1. This allows the neural network to be a lot more efficient, and it allows the data to be more easily processable. Okay? So how do we normalize our data? This is how we do it. We say train images equals train images, and we divide the pixel values by 255 because the range is between 0 and 255. And then to get the values between 0 and 1, what we do is we subtract 0.5. So 0.5, and that's how we can ensure that the values are between 0 and 1. All right? The reason why we subtract by 0.5 is because, let's say we had, some float here that's not an integer, and we get a decimal point after the after the, like, a decimal point. So if we said if it was, I don't know, 64 divided by 255, that's not a whole number. So we need to subtract 0.5 so we get an under whole number, and then we round it because of integer division. So the same thing applies to test images. So we do the same thing for test images. Okay, and we can just copy this. So that's how we ensure our values are between 0 and 1. Okay, so that's normalizing our data. Normalizing our data. Let's write that down. Normalize our images. All right, just so we know what we did. And let's move this up. This is what I like about Keras. You can really easily label what you did. Let's make this bold. Strong, bold. Let's make sure no one has any questions. All right, cool. So, okay. We've normalized our images, but they're still 2D arrays, and neural networks have a hard time accepting 2D arrays. So what can we do to change that? We can flatten our images. Flattening our images from a 2D array to a one-dimensional array. Okay? How do we do this? So the way we do this is we leverage a method called reshape. All right? So we will say, we use the same format here. We'll say train images equals train images dot reshape. Okay? -1 and 784. What does the reshape method do? If anyone wants to participate in the chat, could you put in the chat what do you think the reshape method does, like practically, besides reshaping the image? What does it do? So while I'm waiting, I'll describe it, and if anyone has a good guess in the chat, let me know. So what reshaping does is it takes an array of a given size and literally changes the dimension. All right? So right now we have a 2D array with a size of 784. We need to reshape it from a 2D array to a 1D array. So hence the -1 and the shape 784. And we do the exact same thing for test images. All right, so you see how we're doing these manipulations to both the train images and the test images? That's really important because we want to make sure that our data is the same across the testing and training, so we don't have any errors with the formatting. That's really important that we get the formatting right. Okay? All right, so great. Now we have flattened our images. So we can say flattened images. So we are basically done with data processing. That's it. That's the beauty of working with all these libraries. It's so easy to process, flatten, normalize our data really quick. We did that in what? 4 lines of code. We imported our data in 4 lines of code. We processed our data in 4 lines of code. And in total, we've written 13 lines of code. And we've gotten this far. That's really impressive. Definitely pat yourself on the back at home. Really good job. So now, it is time to build our model, build our neural network. This is probably what you clicked on the video for, building the neural network. So bear with me. Again, if you have any questions, leave them down below. All right. So building the model. The way we build a model, it's super intuitive. We say model equals. Now, remember, we imported at the beginning the sequential model, okay? So we're just going to say model equals sequential. If you want to know what sequential means and some of the activation functions and loss functions, metrics, all of that stuff I'm going to talk about, all of that jargon. If you don't really know what that means, definitely go to my machine learning tutorials playlist, and there's a video that talks about neural networks from scratch, and all of that is described. I have a bunch of videos on neural networks and how they work. Definitely look at my playlist to check out videos that talk about that a little bit more in depth. But today I just want to spend some time on the code specifically and less explaining the jargon as much. All right, so we build our model as a sequential model. Our model will have 3 layers, all right? They're all going to be dense layers. Dense layers, again, are just the simple, fully connected neural network layers. There's nothing unique about them. Neural networks are unique, but there's nothing unique about these layers. How do we create layers in this model? So we say model.add, all right? First, we say the type of layer, dense, and then we say how many nodes in the layer. The nodes, in this case, when we're processing images, the dimensions of the image. 64 by 64 dimensions of our image, all right? So 64, and then our activation function is ReLU. This is another way that the neural network kind of processes inputs to make the prediction process a lot more easy for the algorithm, all right? And again, in the previous videos I described a few minutes ago, ReLU is described in depth. So the last thing we need to say is the input shape, all right? So the input shape, like how many images, the shape of the input, how many images are we processing, all right? The input shape, 784, all right? Now, we need to do this again. So we're having 2 of these layers. So we repeat this layer twice. And then our last layer is the layer that outputs a prediction. The dimension of a prediction is not 64. There aren't 64 different values that we can use, that we can output. Really, there are only 10 values we can output. We can only output 10 values. Why? Because in the data set that we looked at, there are values from 0 to 9. So values from 0 to 9, that's 10 different values. So the way we denote that is, instead of saying 64, we just simply put 10. All right, 10. And then our activation is different to account for we're making a prediction. So the activation function we're going to use is softmax. And that's it. We built our model. So congratulations, tap yourself on the back. You built your first neural network model. All that's left is compiling it, fitting the model, evaluating it, printing out the accuracy, and then using the model. That sounds like a lot, but it's not going to take a lot of code, and it's going to be pretty easy. You just wait and see. So we will write, we keep labeling our code. We're going to say built model. All right. Built model. Now, a few steps left. So basically now what we need to do is we need to tell the neural network, how are you evaluating loss? What metrics are you using? And then print all of that out and also say how long is it going to take, like how many iterations are we running this neural network? How long do we want the neural network to learn? All right. How many images do we want to look at? Do we want to look at 10, 20? So you're going to see all of this in the compile and fit methods of our model. So first, compile. So compiling the model is just getting everything in order, saying how are we evaluating the model with what loss function. All right. And also, all right, so our optimizer, we're going to use our Atom optimizer. Okay. Now, compiling our models. We need to do, like, why is compiling a model important? We need to specify our optimizer. We need to control the learning rate that we're using. In this case, we don't really need to specify their learning rate. There's a default learning rate. Atom is a good choice for optimizers, and again, some of my videos describe exactly why. Compiling takes literally one line of code, and it's really easy. Optimization is trying to create a neural network that is the most efficient as possible. Basically is the most efficient as possible and uses the least, the least processing as possible. That's the easiest way I can explain it. So we've said our optimizer. Now we need to describe how we're evaluating loss, and we'll use categorical cross entropy to evaluate our loss. Okay. And this is just a loss function, just like we had mean squared error as a loss function. There are a million different loss functions, and the compile method accepts a million loss functions. In this case, we're just going to use categorical cross entropy, and later, once we build our model, we can actually play with what our accuracy looks like with different loss functions. And the last thing is metrics, right? So what metrics are we actually evaluating? And we want to look at the accuracy of our model, right? So we say metrics equals accuracy, okay? And then we want to make sure that we're adding commas in between these. That's really important. Make sure accuracy is spelled right. Okay. And that's it. Now we need to fit our model. So we need to say, okay, here is the train images, here's the train labels, here's the amount of epochs I want to run for, here's the batch size, run, go. All right, so model, so we need to do model.fit. We need to, train images is one input, train IMGs, two categorical, what we imported here. This allows us to send the labels into the fit method. And so it will use these labels to evaluate the accuracy of the model. Train labels. Then we need the amount of epochs we're going to run our model. For now, we will say, I think 10 epochs is good. I don't think we need more than 10 epochs. And then finally, we need our batch size. I'm going to say for our batch size, and we can play with all these numbers. For our batch size, we'll say 64 images. All right? Now, the last thing we have to do is evaluate our model. So we've compiled our model, fit our model. Last thing is evaluate our model. I just want to run this and make sure that there are no errors. And if there are any errors, I'll fix them. Oh, so I didn't run this code before, so let me run this really quick. All right, now this should work. Oops. I think I might have, I added this accidentally. That's my bad, everybody. It's a mistake by me. Added this accidentally. I'm just seeing that I miswrote some things really quickly, so I want to do some to make sure everything is okay. Just some error handling here. So one second, guys. Hey, Ron. Thanks for being on the live, bro. All right, let's look at what's going on here. I just want to go through the code and make sure everything's okay. Let's adjust the batch size number to 32. Epochs to, let's 5. Let's see if that changes anything. Alright, so in user code, input 0 of layer sequential is incompatible with the layer. Expected access -1 of input shape to have value 784, but received with 32, 28, 28. It seems like there is a problem with the input size, so let me just take a look at that really quick. So I'm gonna let me rerun everything to make sure everything is okay. Okay, there we go. I reran everything. Everything's good. I was getting a little nervous there. Here's our model evaluating itself. So it's running 5 epochs with a batch size of 32. So it looks like we're getting an accuracy of 96.5, but I think if I increase the amount of epochs we have with a larger batch size, we might be able to get a higher accuracy with a lower loss. And it seems like that's what we're doing. But it looks like it's kind of hitting a certain mean. We'll see if we can get a higher accuracy. The accuracy we got before was 96.5. And this looks like we're going to get to 98.4. That's awesome. So you see how we adjusted the amount of epochs and the amount of images that we're using for training, and we got a higher accuracy number. 98.4 is super impressive for a model with literally 3 layers. All right, so now let's add a markdown here, and we compiled and fit the model. Great. All right, so the last thing we have to do is evaluating the model, seeing how well it did with our test data, then saving the model, and then we want to use it later on. So let's say we want to use it somewhere else or a different time or different place. How do we do that? So let's finish off this tutorial. So to evaluate our model with our test results or our test data, we say model.evaluate. Our inputs are test images. And then we do the same thing, 2 categorical for our test labels, okay? Make sure I spell evaluate right. All right, now we'll run this. All right, so we got a loss value that was slightly higher. So if we look at the loss value here in our last epoch, we got a loss value of 0.04 with an accuracy of 98.4. Here we got a loss value of 0.09 with an accuracy of 97.3. That is super impressive. Again, for a model we wrote in 4 lines of code. All right, last thing we have to do is save the model. So the way we do this is say model.save weights model.h5. That's the type of model. And if we do that, model.save weights h5, we can retrieve that file. Use it later on. Now let's say we want to make predictions. All right, so we would create a variable called predictions, and we actually have a function in model. We say model.predict. And then with model.predict, we can input test images or test images, basically, or train images, but we want to use test images. And we can say, I want to evaluate test images from index 0 to 10, or index 0 to 12, or index 1 to 13, whatever. So let's say we want to evaluate indexes, like test images from 0 to 10. We want to see, for 10 images, can our model get it right? With 98% accuracy, I really hope so. All right, so let's redo that. I'm going to put this in a different line of code so we don't have to, different cells, so we don't have to run that over and over again. So pred is model.predictions with our first 10 images. Let's print pred. So let's just say pred. All right. So predictions on its own are all of these numbers that we can't, we don't know how to interpret. So to print our model's predictions, we need to do a little bit manipulation with NumPy. The way we do this is we print np.argmax, and then our arguments are predictions and axis equals 1. And this allows us to process our data, take the argmax, which is a mathematical function, of our predictions and output them from 0 to 10. And if you can tell here, there's data for 10 different images. So the 10 images we want to predict. So if we print that out, we should get the first 10 images. All right, those are our predictions. 721041495 Those are the numbers we predict for the test images. Now let's see if that's actually correct. So how do we see if this is actually correct? We would go to test labels, and if we just print test labels, we get an array of a bunch of different numbers. All right, but we only want to print test labels for the first 10 images. And look at that. Those arrays are the exact same thing, which means that our model successfully predicted the numbers within the images. Okay? So that is amazing. So I wonder if we print test images, what this will output. All right, so this will output an array, obviously, because we normalize the data between 0. Oh, these are negatives. I believe. Oh, I think I'm printing out an array of the different values of the labels. I'm not exactly sure what this prints out, but as you can see, we've been able to successfully predict the numbers within the images, the handwritten digits, successfully. So let's review what we did. What we did was we imported all of these libraries. We assigned 4 different variables: train images, train labels, test images, test labels. We normalized our images by dividing the pixel values by 255 and subtracting by -0.5, subtracting by 0.5. And did the same for test. Then we flattened our images by reshaping them from 2-dimensional arrays to 1-dimensional arrays. Then we created a neural network with 3 layers. This 3-layer neural network was fit over 10 epochs and evaluated or trained on 64 images, and was able to produce an accuracy of 98.4%, which is phenomenal. And then we tested that, and we were able to see that our model predicts pretty darn good for the first 10 images perfectly without any mistakes. So thank you guys for watching. I really appreciate you. I tried this live format. I hope you guys liked it. Thank you so much for watching, and I will see you in the next one. Make sure to subscribe if you aren't already. Peace.